this hypothetical. So
17. In the 20th century, daily
now
life
let's
has
go
been
back into a little
revolutionized
bit
with
of
the
math.
help of small, compact electric motors of less than 1 horsepower. 90% of all motors built today, they quietly and efficiently power our tools, our car windows, and most of our world.
So the electric motors, how do they work? We know something about magnetism, obviously. You got the north and the south poles. You get a magnet suspended through a string. It's going to line itself up along the direction of the Earth's magnetic field. The end pointing towards the north is the North Pole. The end pointing towards the south is going to be the South Pole. You can map the magnetic field using a compass. Compass is a magnet and a pivot. So by using a compass, you would notice that the magnetic field lines are starting at the North Pole and they are pointing towards the South Pole. We already had a discussion regarding the Earth's magnetic field. We don't know exactly how it comes about. We know that the currents generated, and within the Earth you have these conduction currents, which means that you got the molten metal just traveling this way and that way, and then if it's charged, obviously it's going to be causing currents. When you get a magnet and break it into smaller and smaller pieces, you know that it doesn't matter how small the pieces are, it's always going to be magnetized. We also know that the magnetism originates from within the atoms. Within the atoms, you have a microscopic current loops. The microscopic current loops will be responsible for the atoms to become magnetized. So the atoms become small magnets. All right, so one of the observations that I'm going to show you is take a look at this. I was going to say green. Holy shit. All right. Blue beam that you guys are looking at, right? All right, so it looks like a blue beam, it looks like a light beam, except when you put a magnet to it, it becomes deflected, which means that the beam that you're looking at is composed of charged particles. If you use the right-hand rule, which works for the positive charges, and if you have negative charges, you end up using your left hand, and then you will get the same results. Immediately, it was discovered that looking at the deflection of these beam, it was composed of small negative charges. Why did I say small? Obviously, you cannot see these charges. All right, so this is how the electron was discovered. The year is 1887. The guy who discovers it, his name is J.J. Thomson. He wins the Nobel Prize later in 1905, I think, or 1906, because of this experiment. All right, this is known as the cathode ray tube. All right, so that later becomes the TV that you guys are looking at. And this beam is the electron beam that we trace onto the screen when the first TV was built. All right, so that's the story of it. All right, so we got this electron beam. All right, let's check to see how this is going to work. So by using a magnetic field, you can deflect.
These are the charged plates in a cathode ray tube. Here's one that's on the top. Here's one that's on the bottom. And a stream of electrons comes through that point there. Inside of this case, there's a high voltage grid and a little device that gives off electrons. The electrons see the high voltage, they get accelerated, and some of them pass through a small hole in the center. The ones that pass through come and they will hit a screen. And when those electron beams hit the screen, causes it to glow. If I were to apply a positive voltage to the top plate, as the negative electrons went through, they would be deflected. They would go upwards as a result of that positive voltage. On the other hand, if I were to put a negative voltage on the top plate, the electron beam would go downwards as a result of that. I can alternate the beam electrically, alternately going up and down by altering the positive and negative aspect of that beam. This is the fundamental principle in the operation of television. I get a device that causes it to deflect up and down, vertical. I can also do the same thing horizontally with two more plates that control the horizontal axis. And by combining the two, I get 45 degrees. Now, as the charged particle travels through the air, kind of it acts like an electron going through a wire in as much as it creates a magnetic field around it. If I were to bring a magnet nearby, I could deflect the beam with a magnet. This is
So
cool.
he's able to deflect the beam. That's the electron beam. And
Electricity and magnetism inexplicably connected.
all right, so moving forward. All right, so charge at rest doesn't experience a magnetic force. Charge moving along the direction of the magnetic field does not experience a magnetic force. Charge going across the magnetic field will experience a force, magnetic force that's going to cause it to become deflected. All right, so use the right-hand rule to figure out the direction of that force. So this is the right-hand rule from this that we're using. All right. So mathematically, how does that work? All right, so it's going to cause a deflection. All right, because we have to switch back and forth.
Welcome to the demo prep room. We're sitting here in the dark because we're going to show you that the charged particle beam does indeed go in a circle when you put it in a uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun in it. An electron gun really just means a heated metal filament that's easy to draw electrons off of. Near the gun that you can now see glowing orange is a little metal plate that we put at a large positive potential. So that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on.
So you
until it
guys
hits
can see the
glass.
beam right here.
Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. So you're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam. If you bring in a strong, concentrated magnetic field. But what we're here to do is to create a uniform field, and that's what these two big coils are. So this is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here, when we start turning it up, and you can see it's starting to curve.
Okay, this is not the current that
more and
you're
more.
interested in.
And right now it looks like it wants to make a circle, but the
portion of
radius is too
individual
big. It
electrons.
doesn't fit in the bulb. So if I keep turning it up, more and more current, bigger and bigger B field. Eventually, there it is. It makes a circle. Perfect circular motion, going right back to where it started. I'm going to turn the magnetic field.
All right, he was able to create a perfectly circular motion using electrons, kind of like this, guys. This is problem number 1 from the handout. All right, so once again, you have a proton, so you got your positive charge. It's starting from rest, and you get a parallel plate capacitor that's known as the electron gun. So the parallel plate capacitor is going to be used to accelerate the charged particle. Potential difference between the plates is going to be 2100 volts. And then what happens is protons will leave the capacitor through a hole. You got a small hole. And outside of the capacitor, you will have a constant magnetic field region. So here's the strength of the magnetic field. So a couple of things that we need to figure out. We need to figure out the speed of these charges as it leaves the capacitor. And then find the change in the proton's kinetic energy inside the magnetic field. And then find the radius of the circular path. So that's what we need to do. All right, so those are the things that we will have to figure out. All right, so this is in reference to problem number 2. Proton is going to be accelerated through a capacitor, through a potential difference. So into a constant magnetic field region. In this case, the magnetic field is pointing into the page, so proton is going to go into a counterclockwise circular motion. We got 2 questions. A is going to be the speed of this proton upon exiting the capacitor, and C is the size or the radius of the circle. is straightforward, the speed of a proton. Obviously, acceleration is going to be caused by a voltage or potential difference of the capacitor, which is going to be caused by a conservative force field like the electrostatic force field, which means that the mechanical energy is going to be constant. Initial mechanical energy is all potential energy. The final is going to be all kinetic. So the only thing you have to do is solve for the speed. And once you come up with the final expression, we know that the potential difference is going to be 21,000 volts. Charge is a unit charge for the proton, and you got the mass of the proton. Just plug those into the final equation. We will skip part B for now, and we will move on to part C. In part C, we're gonna try to figure out the radius of the circle. We know that the proton is going to be captured by the magnetic field, and it's going to go into a circular motion in the counterclockwise direction. So let's just reverse the direction. And this circle is going to have a radius, so the question is, what is the radius? What's causing the circular motion is the centripetal force. In this case, the centripetal force is the magnetic force. The angle theta is the angle between the velocity vector and the magnetic field, which happens to be 90 degrees. So sine of 90 is going to be 1. Now from this expression, you can isolate the radius, which is r. And then this is the final expression that you come up with. So we know the mass of the proton, we know the charge, we know the strength of the magnetic field. We also know how fast the proton is moving upon entering into this region. So the question is, what happens to the kinetic energy of the proton inside the magnetic field? So how much does the kinetic energy change inside the magnetic field? Angle in this case, the angle between the centripetal force and displacement vector, and the object is getting displaced along the direction of motion. So force does not have a component along the direction of displacement, which means that the force does not contribute to motion, which means that no work is being done on the proton, but that means no energy is being transferred. Alright, so problem number 3, I'm gonna, instead of doing the one from the handout, I decided to extend problem number 2 into problem number 3. We know that the proton is going to move in a circle at a given speed at a given radius. So the question is, what is the period of this motion as well as the frequency of this motion? Here's what we know. We know the speed is related to distance over time. Distance is the circumference, the time is the period. The period is the time it takes for it to actually complete a single circle or cycle in this case. We know the speed. We came up with an expression earlier, so that's the expression that we will get to use. The only thing we have to do now is just isolate t, which happens to be the period, and plug in the terminology. Frequency is the reciprocal of a period. That's the number of periods per second, where the number